Sometimes, looking at a map of the solar system, one cannot shake off a strange feeling of intentionality. Everything is too complex. Small rocky planets are grouped near the Sun, then an ideally located asteroid belt, like a border zone, and beyond it, majestic gas giants in wide, stable orbits. As if some invisible architect designed this system, placing everything in its proper place. Of course, we are not talking about intelligent design, but science increasingly concludes that such an architect did exist. One object, whose gravity in the dawn of time acted almost like a conscious will. It cleared some orbits and polluted others. It did not allow a fifth rocky planet to form. It possibly determined the mass of Mars. It both protected and threatened the young Earth. The name of this hidden conductor is Jupiter. Its incredible size is not a coincidence, but the primary cause of all the order we see around us. So what is this conspiracy of physical laws that allowed it to become so big? Let's figure out why Jupiter is so big. We need to start not with Jupiter itself. We need to start with emptiness, with the cold, dark, almost absolute emptiness that was here, in place of our solar system, approximately 4.6 billion years ago. This is the starting point, the primordial canvas on which cosmic forces began to paint their picture. And this canvas was huge. Just imagine a giant amorphous cloud stretching for tens of light years. It was so rarefied that if you were inside it, you wouldn't even realize you were in a cloud. The density there was billions of times lower than in the best vacuum we can create in terrestrial laboratories. And the temperature was close to absolute zero, only about 10 to 20 degrees on the Kelvin scale. It is a world where the movement of atoms had almost stopped. This is what astronomers call a giant molecular cloud. But here's the most interesting thing. Despite its apparent emptiness, this cloud contained absolutely all the building materials from which the Sun, Earth, we ourselves, and of course, Jupiter itself were subsequently created. And the composition of these materials is perhaps the most important key to our mystery. If we could take a sample of this primordial substance and analyze it, we would see a surprisingly simple picture. Approximately 98% of it consisted of just two elements, hydrogen and helium. These are the lightest, simplest, and oldest elements in the universe. They were not born in stars. They were born in the first minutes after the Big Bang, almost 14 billion years ago. This, if you will, is the primordial broth, the legacy of the very birth of the cosmos. 98% of all visible matter is just them, hydrogen and helium. But what about the remaining 2%? And this 2% is the most interesting part. It is everything else. Everything that we see in the periodic table that is heavier than helium. The carbon that makes up our bodies, the oxygen we breathe, the iron that flows in our blood, the silicon that makes up the rocks beneath our feet. Astronomers, with their characteristic conciseness, call all of this by one word: metals. Although, of course, it's not just about metals in the usual sense. Where did this 2% dust come from? It is the product of death. It is the ashes of long extinguished stars, a generation of massive celestial bodies that lived and died billions of years before the birth of our sun, were giant nuclear furnaces. In their depths, under colossal pressure and at incredible temperatures, light nuclei of hydrogen and helium fused into heavier ones. This process is called stellar nucleosynthesis. A star lives, it creates carbon, then oxygen, neon, magnesium, and so on, up to iron. And then, when the fuel runs out, the most massive of these stars explode. They explode as supernovae. And in the blinding fire of this explosion, lasting only a few moments, elements even heavier than iron, gold, platinum, uranium, and all this precious stardust are born. All this result of the alchemy of entire generations of stars is ejected into interstellar space. Our molecular cloud was precisely such a repository. It was a huge reservoir of primordial hydrogen and helium, slightly contaminated with the ash of stellar crematoria, 98 parts of ancient gas and 2 parts of stardust. Remember this proportion, it will be crucial for our entire story. So, we have a cloud. It is cold, rarefied, and stable. It could have drifted in this state for millions more years. Something had to disrupt this equilibrium, something had to give it a push. Scientists believe that such a trigger was most likely a shock wave from a supernova explosion somewhere nearby. This wave, sweeping through the cloud, compressed some of its regions. And here, the main force in the universe came into play: gravity. Gravity is a strange thing. It is incredibly weak, but it has two unique properties. It acts over any distance, and it always only attracts. In normal conditions, the pressure of the gas inside the cloud successfully resisted the weak gravitational pull of its particles. But once the shockwave created a local condensation, the scales tipped. In this condensed region, gravity became slightly stronger than the pressure, and a process began that could no longer be stopped. This clump began to compress under its own weight, and the smaller it became, the denser it was, and the stronger its gravity became. And the stronger the gravity, the faster it compressed. This was a self-reinforcing, avalanche-like process that physicists call gravitational collapse. Over hundreds of thousands of years, the central part of this clump became hotter and denser until a thermonuclear reaction ignited in its core. A protostar was born, our sun. But we are not interested in the sun itself right now, but in what remained around it. Not all the matter of the cloud fell into the center. The part that had even minimal initial rotation could not simply fall in a straight line, it was spun. Here, the fundamental law of conservation of angular momentum operates. This is the same law that makes a figure skater spin faster when they pull their arms in. As the cloud compressed, its rotation accelerated, and under the action of centrifugal force, this rotating cloud of matter flattened. It turned into a giant rotating disk. Astronomers call this object a proto-planetary disk. This is the birthplace of all planets. Imagine a giant vinyl record, with a young, not yet fully formed sun shining in the center. This record stretches for billions of kilometers. It consists of the same 98% hydrogen and helium and 2% dust. But now, these materials are not scattered chaotically. They are organized into a rotating structure. It was in this disk, in this cosmic dance of gas and dust, that Jupiter's story began. Everything it is today was predetermined here. Its colossal size is a direct consequence of the conditions that prevailed in this disk 4.5 billion years ago. It is important to understand Jupiter had no secret source of matter. It was molded from exactly the same material as Earth, Mars, or any asteroid. The difference was not in what, but in where and how. It was not uniform. Near the young sun, it was very hot. Temperatures reached 1,000 degrees. Further from the center, it became colder and colder. This temperature gradient is another key element of our puzzle. It created invisible boundaries that determined which materials could be used to build planets in different parts of the system. So, let's summarize this chapter. We have set the stage. We have a central star, the young sun. Around it, a giant disk of gas and dust rotates. We know the exact recipe of this disk. 98% is the legacy of the Big Bang and the ash of ancient stars. And we know that there is a critically important temperature drop in this disk. All conditions for great construction are created. Billions and billions of tons of building material are circling in a giant vortex. Somewhere there, in this chaos, the foundation of the future giant has already been laid. But for it to start growing, something special had to happen. Some line had to be crossed, an invisible line that divided the solar system into the kingdom of rocks and the kingdom of ices. We have a young sun and a giant disk of gas and dust rotating around it, a proto-planetary disk. We even know its exact composition. 98% hydrogen and helium and only 2% heavier elements, which we conventionally call dust. It would seem the material is the same everywhere. Why then did the planets turn out so different? Why did small rocky worlds arise in one part of the system and colossal gas giants in another? The answer lies not in the composition of the disk, but in its physical conditions. And the most important of these conditions is temperature. Let's imagine this disk again. In its center burns a young, furious sun. Its radiation heats the inner regions of the disk to 1,000 degrees. The further from the center, the colder it gets. At Mercury's orbit, there is hellish heat. At Earth's orbit, it is much cooler, and somewhere far away in the backyards of the forming system, the temperature drops to chilling values close to absolute zero. This smooth temperature drop, which scientists call a temperature gradient, is the invisible sculptor that shaped all the planets as we know them. To understand how it did this, we need to take a closer look at our dust, at those 2% of matter that are not hydrogen or helium. This dust can be conventionally divided into two large groups. The first group consists of refractory compounds. These are silicates, that is, essentially compounds of silicon and oxygen, which make up ordinary rocks and metals, mainly iron and nickel. Their main property is that they remain solid even at very high temperatures. They can melt, but it takes truly extreme heat to turn them into gas. Therefore, throughout the protoplanetary disk, from its hottest parts to its coldest, these substances existed as tiny solid dust particles. This was a universal building material, available everywhere. But the second group is a completely different story. These are volatile compounds, mainly water H2O, as well as methane and ammonia NH3. On our Earth, we are used to seeing water in three states: solid, liquid, and gaseous. But under the conditions of vacuum and low pressure in the protoplanetary disk, it essentially had only two options: either be a gas, i.e., water vapor, or be a solid, i.e., ice. The liquid phase was practically impossible there. And here's where it gets interesting. The fate of these volatile compounds depended entirely on temperature. Near the young sun, where it was hot, all the water, all the methane, and all the ammonia were in a gaseous state. They were part of a huge gas ocean, mixed with hydrogen and helium, and could not participate in planet building as solid material in any way. But as one moved away from the sun, the temperature dropped, and at a certain distance, it fell to a critical point. For water, this point is approximately 150 to 170 degrees on the Kelvin scale. That's about minus 120 degrees Celsius. When the temperature in the disk fell below this value, something magical happened. Water vapor molecules began to slow down and stick together, forming tiny ice crystals. Condensation occurred. Gas turned into solid. That invisible boundary in the protoplanetary disk, beyond which the temperature becomes low enough for water to condense into ice, is called the frost line in astronomy, or more poetically, the snow line. This was not some clear line drawn in space. Rather, it was a blurred zone, but its significance for the entire subsequent history of the solar system is impossible to overestimate. It divided the disk into two completely different worlds. The inner world, located within the snow line, was the realm of rock and metal. Here, only refractory materials were available for planet building, and they, as we remember, were very few. They accounted for less than 0.5% of the total mass of the disk. But the outer world beyond the snow line was completely different. There, to the same rocks and metals, a new abundant building material was suddenly added: water ice. How abundant! To understand this, we need to remember what stars and the universe as a whole are made of. After hydrogen and helium, the most common elements are oxygen, carbon, and nitrogen. Silicon and iron are much lower on this list. This means that in the protoplanetary disk, there was much more oxygen than silicon. And since that's the case, there was several times more water, which consists of hydrogen and oxygen, than all silicates and metals combined. Let's use a simple analogy. Imagine you want to build a castle. In the first case, inside the snow line, you are on a dry, stony beach. You only have sand and a little gravel. You can sculpt a small castle, but it will be a long and laborious task, as there is very little material. Now the second case. Beyond the snow line. You are on the same beach, but in winter, during a heavy snowfall. You have the same sand and gravel under your feet. But now a thick, sticky layer of snow has fallen on top of them. And there is much, much more snow than sand. Now you can build not just a castle, but a huge snow fortress. And you will do it much faster because you have an abundance of building material. The snow line did exactly that. It increased the amount of available solid building material by 3 or even 4 times. This changed everything. Inside this line, the seeds of planets, called protoplanetary cores, had to form exclusively from rare refractory dust particles. The process was slow. Colliding, the dust particles stuck together, forming small clumps, then kilometer-sized asteroids, or as they are called, planetesimals. And it was these planetesimals, colliding with each other over millions of years, that gradually assembled into something planet-sized. Thus were born Mercury, Venus, Earth, and Mars. This is a long and inefficient process, which is why they remained relatively small. But outside, in the realm of ice, Everything went according to a completely different scenario. There, the future Jupiter began its growth in conditions of incredible abundance. Its seed formed not only from rocky dust, but also from countless ice crystals. They were everywhere. They actively stuck to each other and to rocky particles. The process went much faster and more efficiently. If in the inner part of the system a modest sand castle was being built, here a giant snow fortress was being erected. According to calculations, the snow line in our solar system passed at a distance of approximately 2.7 astronomical units from the Sun, that is, 2.7 times farther than Earth. Today, this place is the inner part of the asteroid belt, and Jupiter, as we know, is much farther away, at a distance of approximately 5.2 astronomical units. That is, it was born and grew in the very heart of this snow paradise. Its location gave it a colossal advantage. It gained access to huge reserves of solid material, which allowed its core to grow to impressive sizes in a very short time by astronomical standards. And this speed, as we will see in the next chapter, turned out to be a decisive factor. Planet formation is not only construction, it is also a race against time. So, we have solved the first part of the mystery. Jupiter became big because it was born in the right place, far beyond the snow line, where the cold of space allowed water to freeze and become the main building material. This gave it a huge head start compared to its rocky neighbors. It was able to quickly accumulate mass, molding a giant core from a mixture of rock and ice. But this is only half the story. After all, today Jupiter is not an icy planet, it is a gas giant. 90% of its mass is that very hydrogen and helium from which the primordial disk consisted. How did it, having begun its journey as a giant snowman, manage to attract this immense gas ocean? How did the icy core turn into a gas king? This is the next, most dramatic stage of its birth, which we will discuss further. So, we found out that Jupiter ended up in the right place at the right time. It formed beyond the snow line in a world where ice was abundant. This gave it a huge advantage and allowed it to start building its core much faster and more efficiently than the inner planets, which had to content themselves with only scraps of refractory materials. But how exactly does this construction happen? How can an object the size of a planet grow from billions of microscopic dust particles and ice crystals less than a millimeter in size? This process is one of the most complex and still not fully understood in modern planetology. But the main theory that best describes the birth of planets today is called the core accretion model. Let's break it down step by step. The word accretion comes from the Latin accretion, which means growth or increase. And this word perfectly describes the essence of the process. Everything starts small and gradually grows. Imagine a proto-planetary disk. It is a turbulent place. The gas and dust in it do not just orbit the sun in perfect circles. They are in constant chaotic motion, similar to Brownian motion. Microscopic particles, silicate dust, and ice crystals constantly collide with each other. At this stage, gravity is still too weak to play any role. The particles are too small. Instead, other forces act. When two dust particles collide at low speed, they can simply stick together. Electrostatic forces, similar to those that make dust cling to a TV screen, or van der Waals forces, weak intermolecular attraction, operate here. Thus, dust particle by dust particle, crystal by crystal, larger aggregates begin to form, like dust bunnies collected under the bed. These loose, fluffy structures, resembling snowflakes or soot flakes, gradually grow, reaching sizes of several centimeters or even meters. But here arises the first serious problem, which scientists call the meter barrier. The fact is that objects about a meter in size experience very strong resistance from the surrounding gas in the disk. The gas orbits the sun slightly slower than solid bodies due to its own pressure. And for meter-sized rocks or ice, this gas becomes like a viscous syrup. It slows down their movement, causing them to spiral into the sun and fall very quickly, according to calculations, in just a few hundred or thousand years. If this mechanism were the only one, then all these objects would simply burn up in the star and no planets could form. How did nature overcome this barrier? Today, the dominant hypothesis is known as streaming instability. It sounds complicated, but the essence is quite elegant. Imagine a stream of water carrying sand. In some places, Due to turbulence, local accumulations of sand can form. Something similar happens in a protoplanetary disk. The interaction of solid particles with gas creates regions of increased concentration in the disk. These centimeter and meter-sized pebbles. They begin to move together, like a school of fish or a swarm of bees. And it is in these dense accumulations that gravity finally comes into play. The gravitational pull of these swarms becomes sufficient to overcome all other forces. They begin to compress under their own weight, and direct gravitational collapse occurs. In a very short time, possibly just a few thousand years, these swarms of particles compress into solid bodies tens and hundreds of kilometers in size. These are planetesimals. In translation, infinitely small planets. These are no longer just dust clumps. These are real cosmic mountains, made of a mixture of rock, metal, and, in Jupiter's case, a huge amount of ice. The solar system at this stage resembled a giant billiard table, littered with millions of such objects. Now accretion enters a new level. Gravity becomes the main driving force. The planets of Zamali begin to attract each other. Their orbits intersect, they collide. Sometimes collisions lead to destruction, but more often, especially if the speeds are not too high, the larger object attracts and absorbs the smaller one. This is a brutal process of gravitational natural selection. The one that is larger survives and grows. In each zone of the protoplanetary disk, leaders emerge over time. The largest planets of Zamali, which begin to dominate their surroundings. They grow faster than all others because their gravitational vacuum cleaner becomes increasingly powerful. They clear their orbits by absorbing or ejecting smaller neighbors. Such leaders are called planetary embryos or protoplanets. The future Jupiter was exactly such an embryo. But thanks to the abundance of icy material beyond the snow line, its growth was truly phenomenal. Where the embryo of Earth slowly collected silicate crumbs, the embryo of Jupiter greedily absorbed not only stones, but also giant icy planets of Zamali, which were several times more numerous. This process continued for millions of years. Protoplanet Jupiter grew, accumulating mass, and densifying under its own gravity. In its center, a dense core of heavy elements, stones, and metals formed, which settled down, surrounded by a giant mantle of compressed ice, water, ammonia, and methane. And here we come to a turning point in the entire story. To launch the next, most grandiose stage of its formation, Jupiter's core had to reach the so-called critical mass. This idea was first developed in detail by the Soviet astronomer Viktor Safronov in the mid-20th century, and later developed by American scientists such as James Pollock. According to their calculations, this critical mass is approximately 10 to 15 Earth masses. Why exactly this much? What is so special that happens when the core reaches this mark? The thing is this. While the core was smaller, it certainly had gravity. It could hold a small, thin atmosphere of surrounding gas, hydrogen, and helium around itself. But this atmosphere was in equilibrium. The pressure of the gas, which was heated by compression and by the heat of the core itself, successfully counteracted gravity. As much gas was attracted, about the same amount escaped back into the disk. The growth of the gas envelope was very slow, but when the core's mass crossed the threshold of 10 to 15 Earth masses, the situation changed drastically. The gravity on its surface became so monstrous that no gas pressure could resist it anymore. The equilibrium was broken. The atmosphere began to compress under its own weight, making room for new portions of gas, which rushed to the protoplanet from the disk. And the more gas fell onto the planet, the more massive it became. And the more massive it became, the stronger its gravity became, and the faster it sucked in new gas. An avalanche-like self-accelerating process began, which scientists call runaway or uncontrolled gas accretion. Reaching the critical core mass was like pulling the trigger. Until that moment, Jupiter was just a very large icy ball. It gained mass slowly, bit by bit, for millions of years. But after pulling that trigger, everything changed. It turned into a space vacuum cleaner of incredible power, which, in a very short time, just a few 100,000 years, sucked up almost all the gas from its surroundings, increasing its mass tenfold. Thus, the core accretion model gives us a clear two-stage picture of Jupiter's birth. Stage 1. The slow formation of a massive core of rock and ice, which lasted for several million years. This stage was only possible thanks to its location beyond the snow line. Stage 2. Rapid, almost explosive growth due to uncontrolled attraction of hydrogen and helium, which began after the core reached a critical mass of 10 to 15 Earth masses. This model elegantly and well explains the main features of our solar system, but it poses one very important question. The question of time. How do we know that Jupiter had enough time for all these processes? We will talk about this in the next chapter because, as it turns out, the universe allotted a very short time for the birth of gas giants. In the previous chapter, we left our future Jupiter at a turning point in its history. After several million years of slow and meticulous construction, its core, consisting of a mixture of rock and ice, finally reached the critical mass, approximately 10 or perhaps 12 masses of our Earth. We compared this event to pulling the trigger. Until this moment, the planet's growth was slow, almost linear. But after that, everything was supposed to change. Jupiter stood on the verge of the most dramatic stage of its birth, runaway gas accretion. But here arises a very important, implicit question. The question of time. The core accretion model, for all its elegance, implies a rather lengthy process. First, dust particles must stick together, then planetesimals must form. And only then, after millions of years of collisions, does a massive core grow. But did Jupiter have this time? Is the protoplanetary disk not an eternal and unchanging structure? The answer is a categorical no. The protoplanetary disk is a temporary, ephemeral phenomenon by cosmic standards. It exists only for a brief moment, while a young star goes through its turbulent early years. And this moment is all the time that nature has allocated to create gas giants. It was a real race against time, and Jupiter had to win it. Let's figure out what exactly threatened the protoplanetary disk. Its main enemy is its own parent, the young sun. In the first few million years of its life, a star is not yet as stable and calm a luminary as it is today. It goes through an extremely active phase, which astronomers call the T Tauri stage, after the first object of this type discovered. At this stage, a young star is unstable. It rotates very rapidly. Its magnetic field is chaotic and incredibly powerful. Giant protuberances and flares erupt from its surface, and most importantly, it emits a colossal amount of stellar wind. This is a stream of charged particles flying from the star at speeds of hundreds of kilometers per second. This wind is thousands, or even millions, of times more powerful than the calm solar wind we observe today. In addition, the young sun emits a huge amount of hard ultraviolet and X-ray radiation. This stream of high-energy photons literally bombards the protoplanetary disk. And these two factors, the powerful stellar wind and hard radiation, act like a giant cosmic broom. They begin to systematically destroy the disk. This process is called photoevaporation. Ultraviolet photons heat the gas on the surface of the disk, especially in its upper layers. The heated gas particles gain such high speed that the star's gravity can no longer hold them. They simply fly away into interstellar space, and the stellar wind picks up this evaporated gas and carries it even further. The disk begins to melt like snow under the spring sun, and it melts quite quickly. Astronomical observations of young stars in our galaxy show that the average lifetime of a protoplanetary disk is only from 3 to 10 million years. 10 million years is the absolute maximum. After that, there is practically nothing left of the gaseous component of the disk. Only a small amount of dust and already formed planets remain. Now you see what harsh time constraints Jupiter was under. He had only a few million years for everything. During this time, he had to manage to form his enormous icy core, reach critical mass, and only after that begin to absorb gas. If he had hesitated even a little in the first stage, if the formation of the core had dragged on, say, until 12 million years, then by the time he was ready to start inhaling gas, there would have been nothing to inhale. All the hydrogen and helium would have been irrevocably blown into space by the stellar wind. In that case, instead of Jupiter, there would be just a large icy planet today, possibly resembling an enlarged Neptune, but not a gas giant. But Jupiter managed. He won this race. His core formed quickly, in just 1 to 2 million years, thanks to the abundance of ice beyond the snow line. And when it reached the coveted mark of 10 to 15 Earth masses, he still had several million years to take advantage of the grand prize, an almost untouched ocean of primordial hydrogen and helium, which made up 98% of the mass of the entire disk. And then began the great inhalation, the process of runaway accretion. Let's imagine this more vividly. Imagine that Jupiter's core is a seed with incredible gravity, and the surrounding gas is very fertile soil. As soon as the core's gravity became strong enough to overcome the gas pressure, it began to suck it in like a super powerful vacuum cleaner. But this was not a linear process. It was a chain reaction. Here falls the first 1,000 tons of gas onto the core. The planet's mass increases. Consequently, its gravity also increases slightly. Now it can attract gas even more effectively. The next 1,000 tons fall. The mass grows again, gravity grows again, and so on. The more Jupiter absorbed, the stronger it became, and the more greedily it absorbed again. This is a classic example of positive feedback. This process can be compared to a snowball rolling down a mountain. At first, it is small and rolls slowly, but as it moves, it picks up more and more snow, becomes heavier, rolls faster, and because of this, it picks up even more snow. At some point, its growth becomes avalanche-like. This is exactly what happened to Jupiter. In a period estimated to be only a few 100,000 to 1 million years, it increased its mass tenfold. It attracted more than 300 Earth masses, consisting almost exclusively of hydrogen and helium. It literally sucked up almost all the gas from its part of the solar system, leaving a vacuum behind. This process was so turbulent that the young planet must have glowed like a dim star. The gas falling onto it compressed and heated up to 1,000 degrees, emitting a huge amount of heat. If we could observe the solar system in those distant times, we would see not one, but two glowing points: the bright sun, and next to it, the dim crimson point of proto-Jupiter. It was this final furious spurt that made Jupiter the giant we know. He managed to jump on the last carriage of a departing train. He managed to collect the primordial gas before the sun dispersed it. What about Earth? Why didn't it follow the same path? For two reasons. First, it formed inside the snow line, where there was little solid material. Its core grew much slower. By the time the protoplanetary disk dispersed, it had barely managed to gain its current mass and was nowhere near the critical mark of 10 Earth masses. It lost the race against time. Second, even if it had somehow grown faster, there was much less gas in the inner part of the system. It was hotter and more rarefied. It had no chance of becoming a gas giant. So, the secret of Jupiter's greatness, according to this model, is revealed in two acts. Act 1. Birth in a cold, ice-rich world, which allowed for the rapid construction of a massive core. And Act 2. Winning the race against time, which allowed it to absorb vast amounts of hydrogen and helium before they disappeared. This story seems very logical and convincing. It perfectly explains why the inner planets are rocky and small, and the outer ones are gaseous and large. But in science, it is rare for one theory to reign supreme. There are always alternative viewpoints, other ways of looking at a problem. And in the story of Jupiter's birth, there is such an alternative, a suspect. There is another model that suggests that everything could have happened much faster and completely differently. We have just painted a rather coherent and consistent picture of Jupiter's birth. It was a bottom-up process, from microscopic dust particles to a giant icy core, which then, upon reaching critical mass, attracted a huge gaseous atmosphere. This model, the core accretion model, is currently the mainstream theory in planetology. It is supported by numerous calculations and observations, but it would be dishonest to claim that it is the only possible scenario. Science is a battlefield of ideas, and core accretion has a serious competitor. A model that offers a completely different, one might say, revolutionary view of the birth of giants. This is the model of gravitational or disk instability. If core accretion is a bottom-up process, then gravitational instability is a top-down process. It suggests that a gas giant could have formed not as a result of long and gradual construction, but almost instantly, as a result of the direct collapse of a part of the protoplanetary disk itself. Let's figure out how this could work. Imagine our protoplanetary disk. It is a giant rotating structure of gas and dust. Two opposing forces act within this disk. On one hand, gravity. All the particles of the disk attract each other, striving to clump together. On the other hand, gas pressure and the centrifugal force of rotation. The pressure arising from the temperature and density of the gas tends to expand it, while rotation pushes matter away from the center. Under normal conditions, these forces balance each other. The disk is stable, but what if the conditions change? The gravitational instability model, one of whose main proponents is the American astrophysicist Alan Boss, suggests that under certain circumstances, the balance can be disrupted. For this, the disk must be, firstly, sufficiently massive. It must contain a lot of matter so that its own gravity is significant, and secondly, it must be sufficiently cold. After all, the colder the gas, the lower its pressure, and the weaker it resists gravitational compression. If these two conditions are met, especially in the distant cold parts of the disk, then spiral density waves, similar to the arms of spiral galaxies, can spontaneously arise in it. Within these waves, gas and dust become denser. If the density in one of these clumps exceeds a critical limit, then its own gravity becomes the dominant force. It will overcome both pressure and rotation, and then this giant clump of matter, with a mass of several Jupiters, will begin to collapse under its own weight. This process is very similar to the formation of a star from a molecular cloud, but on a much smaller scale. It is a direct, instantaneous collapse. Instead of millions of years required for core growth, such a proto-giant can form in just a few thousand years. This is practically an instant by astronomical standards. Let's use an analogy again. The core accretion model is like building a house brick by brick. You lay brick after brick, row after row, and after a long time, you get a building. And the gravitational instability model is like taking a giant lump of clay and molding the entire house from it in one movement. This model has several very attractive features. The main one is speed. It completely removes the problem of time constraints that we discussed in the previous chapter. There is no need to worry about whether the core will grow before the disk disperses. The planet forms almost immediately, while the disk is still full of gas and forces. This speed is especially important for explaining some exoplanets that astronomers find around other stars. We discover gas giants that orbit at enormous distances from their stars, tens of times farther than Jupiter from the Sun. In such cold and rarefied regions of the disk, the core accretion model works very poorly. It may take longer than the lifetime of the star itself to gather a massive core there, but gravitational instability, on the contrary, should work even better in such distant and cold regions. So why hasn't this elegant and fast model become the primary explanation for our Jupiter? It has its own serious problems. The first problem is mass. Calculations show that during direct collapse of a clump in the disk, very massive objects, on the order of 5 or even 20 Jupiter masses, usually form. Our Jupiter, despite its giant mass, looks quite modest in comparison. The gravitational instability models struggle to explain why the collapse stopped at exactly 1 Jupiter mass and did not go further. The second, and perhaps the main problem, is composition. If a planet forms by direct collapse of a portion of the disk, then its chemical composition should be exactly the same as the composition of the disk itself. That is, 98% hydrogen and helium, and 2% heavy elements. Moreover, the heavy elements should be uniformly mixed throughout the planet. This model does not predict the planet having any separate dense core. But Jupiter, as we have believed for decades, and as modern data generally confirms, has a core. Its interior is enriched with heavy elements much more than could be expected based on simply scooping up material from the protoplanetary disk. The presence of this core, albeit not as we imagined it, is a very strong argument in favor of the core accretion model. After all, in this model, the core is not a byproduct, but the starting point, the cause of the whole process. So, we have two competing theories. Core accretion, slow, gradual, perfectly explaining the presence of a core and Jupiter's mass, but having some problems with time. And gravitational instability, fast, elegant, working well for some exoplanets, but poorly explaining the presence of a core and the relatively small mass of our giant. Today, most scientists lean towards the idea that the core accretion mechanism most likely worked for the formation of Jupiter and Saturn in our solar system. The conditions in our protoplanetary disk apparently favored it more. However, this does not mean that the gravitational instability model is incorrect. Nature may use both mechanisms depending on the specific conditions in a given star system. But the story doesn't end there. Theoretical models are great, but what does direct observation tell us? Can we somehow look inside Jupiter today, after 4.5 billion years, and see traces of its turbulent birth? Until recently, the answer would have been no. But since 2016, an apparatus has been operating in orbit around the gas giant that has allowed us to do just that. And what it saw there has made scientists reconsider much of what we have just discussed. We have considered two main theoretical models of Jupiter's birth. One, core accretion, suggests that it should have a compact, dense core of rock and ice with a mass of 10 to 15 Earths at its center. The other, gravitational instability, conversely, says that there should be no clearly defined core. For decades, this was a purely theoretical dispute. Looking into the depths of a gas giant, hidden under thousands of kilometers of raging clouds and an impenetrable atmosphere, seemed like an impossible task. We could only build models based on the planet's total mass, its size, and its rotation speed. Everything changed on July 4, 2016. On this day, after a 5-year journey, a NASA automated spacecraft named Juno entered a polar orbit around Jupiter. This is not the first spacecraft to visit Jupiter. Before it were Pioneer, Voyager, Galileo. But Juno had a completely special mission and completely special instruments. Its main task is not to photograph clouds, although it takes stunning pictures. Its main task is to study the internal structure of Jupiter, its gravitational and magnetic field, with unprecedented accuracy. It was gravity that became the key that allowed us to see through the planet. How does it work? The law of universal gravitation tells us that the force of attraction depends on mass. If Jupiter were a perfectly homogeneous sphere, it would attract Juno always equally, and the spacecraft would fly in a perfect elliptical orbit. But Jupiter, firstly, is not a sphere. It is flattened due to rapid rotation, and secondly, its interior is heterogeneous. In its depths, there are areas of different density. Juno flies in a very elongated polar orbit once every 53 days, making a close flyby over the cloud tops at an altitude of only a few thousand kilometers. During these flybys, when the spacecraft is as close as possible to the planet, it reacts very sensitively to the slightest inhomogeneities in the mass distribution below it. If it flies over a denser area of the interior, gravity is slightly stronger there, and the spacecraft accelerates almost imperceptibly. If there is a less dense area below it, it slows down. These changes in speed are tiny, amounting to fractions of a millimeter per second. But on Earth, they can be detected. Scientists send a radio signal of a strictly defined frequency from Earth to Juno. The spacecraft receives it and immediately sends it back. When Juno accelerates, moving towards us, the frequency of the return signal increases slightly due to the Doppler effect. When it slows down, moving away, it decreases. By measuring these microscopic frequency shifts, scientists can reconstruct the spacecraft's speed with fantastic accuracy. And knowing its speed at every moment in time, they can create a detailed map of Jupiter's gravitational field. And this map, in turn, becomes the basis for building models of its internal structure. It's like a doctor using a CT scan to reconstruct a picture of a person's internal organs without making an incision. This is planetary-scale gravitational tomography, and when the first data from Juno were obtained and analyzed, the scientific community was in for a big surprise. The picture turned out to be completely different from what the classic simple model of core accretion predicted. We expected to see the following. At the very center, a small, very dense, and clearly defined core of heavy elements. Immediately above it, a sharp boundary, beyond which begins a giant layer of metallic hydrogen. But the gravitational data showed something completely different. Instead of a compact core, scientists discovered a huge, diffuse central structure. Heavy elements, those same rocks and ice, were not neatly gathered in the center. They were spread over a vast area, extending from the very center almost to half the radius of the entire planet. This structure had no clear boundaries. The density within it changed smoothly. Scientists called it a diluted or fuzzy core, deliocore or phase core. The total mass of heavy elements in this zone is estimated at 20 or even 30, Earth masses, which is much more than predicted. But they do not form a dense lump, but are mixed with a huge amount of hydrogen and helium. This discovery was published in leading scientific journals, such as Nature and Science, and it baffled planetary scientists. On the one hand, it definitively buried the simple model of gravitational instability, as it confirmed that Jupiter's interior is heavily enriched with heavy elements. But on the other hand, it dealt serious blows to the classical model of core accretion. How could such a strange, diffuse hybrid have formed? To date, there are two main explanations for this mystery. The first explanation is catastrophic. It suggests that Jupiter originally did have a standard compact core, formed according to the classical scenario. But in the very dawn of the solar system, when chaos still reigned everywhere, another very large protoplanet crashed into young Jupiter, possibly with a mass of about 10 Earth masses. This was a collision of truly apocalyptic proportions. The energy of the impact was so colossal that it could literally shatter Jupiter's original core and mix its fragments with the surrounding hydrogen at great depth. In fact, what we see today is a scar left by this ancient cosmic catastrophe. The second explanation is calmer, evolutionary. It suggests that no catastrophe occurred. Perhaps the diffuse core is the result of processes occurring in Jupiter's interior right now. Unimaginable pressure and temperature reign in its center, millions of atmospheres and tens of thousands of degrees. Under such conditions, even rocks and ice can not only melt, but partially dissolve in the surrounding liquid metallic hydrogen, similar to how sugar dissolves in hot tea. Powerful convective currents that churn in the planet's interior could have gradually eroded the boundary of the original core, carrying heavy elements upward and mixing them with hydrogen over billions of years. Which of these hypotheses is correct, we do not yet know. Perhaps the truth is somewhere in between, and both processes contributed. But Juno's discovery clearly showed us one important thing. Nature always turns out to be more complex and interesting than our boldest models. Jupiter still holds the secrets of its birth. We thought that by looking inside, we would find answers, but instead, we found new, even deeper questions. And that, perhaps, is the most fascinating aspect of scientific inquiry. The data from the Juno spacecraft have forced us to reconsider our views on Jupiter's very heart, on its mysterious diffuse core. But this core, whatever it may be, is only a small part of the planet. Above it stretches an ocean of matter tens of thousands of kilometers deep. And this ocean hides, perhaps, the most exotic and most important substance in the entire solar system. A substance that is not found naturally anywhere else except in the interiors of gas giants. We are talking about liquid metallic hydrogen. To understand what this is, we need to embark on a mental journey into the depths of Jupiter. We start from the upper cloud layers, where the pressure is approximately the same as on Earth's surface. Here, hydrogen is ordinary gas, consisting of N2 molecules. We dive deeper. Pressure and temperature increase rapidly. Thousands of kilometers below the clouds, the pressure reaches hundreds of thousands of Earth atmospheres. Here, hydrogen is no longer a gas. It is compressed into a liquid state, but it is still molecular hydrogen, a dielectric, meaning it does not conduct electric current. But we continue our descent deeper and deeper. The pressure rises to millions of atmospheres. The temperature exceeds 10,000 degrees. This is hotter than the surface of the sun. And then, at a depth of approximately 15 to 20,000 kilometers, a remarkable phase transformation occurs. Under this monstrous, unimaginable pressure, the hydrogen molecules themselves, N2, cannot withstand it. They break down. The atoms get so close that their electron shells begin to overlap. The electrons, which were previously firmly bound to their protons, detach from them and begin to move freely throughout the volume of the substance, forming a so-called electron gas. This is precisely the transition to a metallic state. After all, what is a metal from a physics perspective? It is a substance in which there are free electrons capable of carrying electric charge. By compressing ordinary hydrogen to the limit, we turned it into a conductor, into liquid metal. Imagine a dense forest where each tree is a hydrogen atom and the leaves on it are electrons. In its normal state, the leaves hold firmly to their branches. This is molecular hydrogen. Now imagine that an incredibly strong hurricane hits this forest, our colossal pressure. The hurricane tears all the leaves from the trees and whirls them into a single vortex. Now the leaves no longer belong to specific trees. They have become common. The bare trunks of the trees are protons, and the vortex of leaves is a sea of free electrons. This is metallic hydrogen. This giant ocean of liquid metallic hydrogen makes up the bulk of Jupiter's mass. It extends from the diffuse core almost to the outermost layers of the planet. And it is its existence that explains one of Jupiter's most impressive features: its incredibly powerful magnetic field. Earth's magnetic field, which protects us from solar wind and cosmic rays, is generated in its outer core, composed of liquid iron and nickel. The so-called hydromagnetic dynamo mechanism operates there. Three things are needed for its operation: an electrically conductive liquid, rapid rotation, and an energy source to maintain convective flows in this liquid. Earth has all of this, but Jupiter has it on a much grander scale. Instead of a relatively small iron core, it has a giant ocean of metallic hydrogen, which is an excellent conductor. It rotates at tremendous speed. A Jovian day lasts less than 10 hours. It is the fastest planet in the system, and it has a powerful energy source, heat, remaining from its formation and continuing to be released through slow gravitational compression. Jupiter radiates almost twice as much energy into space as it receives from the Sun. All the conditions for the dynamo machine to work are perfectly met. Convective currents, i.e., the mixing of matter in this rotating conductive ocean, create and maintain electric currents of colossal force, and these currents, in turn, generate a magnetic field. And what a field! Jupiter's magnetic field is 20,000 times stronger than Earth's. It is so large that if we could see it with the naked eye, it would occupy an area several times larger than the full moon in the night sky. Its magnetosphere, the region of space controlled by this field, extends 7 million kilometers towards the Sun, and in the opposite direction, its tail stretches beyond Saturn's orbit for more than 650 million kilometers. It is the largest and most powerful structure in the solar system after the Sun itself. This invisible armor plays a colossal role in the life of the planet and its surroundings. It captures solar wind particles, accelerating them to near-light speeds and creating radiation belts around Jupiter thousands of times more lethal than Earth's Van Allen belts. This is precisely why all missions to Jupiter, and especially Juno, require such complex radiation protection. This magnetic field interacts with the planet's atmosphere, generating the brightest and most powerful auroras in the solar system, which glow in the X-ray and ultraviolet ranges. It also interacts with Jupiter's moons, for example, with the volcanic moon Io, which ejects tons of sulfur dioxide into space. The magnetic field picks up these ions and forms a giant plasma torus around Jupiter, which rotates with the planet. Thus, Jupiter's incredible size is not just a static fact. It is the cause of the extreme physical conditions in its interior that generate the most exotic matter and the most powerful planetary engine in our system. Its mass creates the pressure that turns hydrogen into metal, and this metallic hydrogen, in turn, generates a giant magnetic field that determines all the physics of space for hundreds of millions of kilometers around. And here we see how everything is interconnected. Great size is not just a quantitative characteristic. It leads to a qualitative leap, to the emergence of entirely new physical phenomena impossible on smaller planets like Earth. This is precisely why studying Jupiter is so important. It allows us to look into a world of extreme physics that we could never recreate in a laboratory. It is our natural proving ground for studying the behavior of matter under conditions that are more like the interiors of stars than our familiar planets. But Jupiter's role is not limited to its internal world and immediate surroundings. Its giant mass has made it not just a passive inhabitant of the solar system, but its main architect. And as modern computer models show, in the dawn of time, this architect was very restless and made grand journeys that forever changed the face of our home. We are accustomed to thinking of the solar system as something static and ordered. Planets revolve in their stable, almost circular orbits like clockwork, and it seems like it has always been this way. This notion of cosmic harmony has been ingrained in our minds since the time of Newton. But in the last few decades, thanks to the development of computer modeling and the discovery of thousands of exoplanetary systems, this picture has been shattered. We have realized that the early stages of any planetary system's life are a time of chaos, instability, and grand migrations. And our solar system was no exception. At the center of this turbulent history is Jupiter again. Its giant mass did not allow it to be a mere bystander. It was the main gravitational player, and its movements determined the destinies of all others. One of the most influential and, it must be said, beautiful theories describing its early adventure is called the Grand Tack hypothesis. The word tack is taken from sailing and means a turn, a change of course. And according to this hypothesis, Jupiter in the dawn of its life made just such a grand turn, which forever determined the architecture of our system. Let's go back 4.5 billion years. Jupiter has just formed. It is a giant ball of gas rotating in the remnants of the protoplanetary disk. This disk, although much more rarefied, still exists. And the interaction of the young planet with this disk leads to an amazing phenomenon: planetary migration. How does it work? Jupiter's gravity perturbs the gas in the disk. It creates spiral density waves in it, very similar to the wake left by a ship. The inner spiral wave, which rotates faster than the planet, pulls it forward, trying to accelerate it and, consequently, push it into a higher orbit. The outer wave, which rotates slower, conversely, slows the planet down, taking away its orbital energy and causing it to spiral inward towards the sun. In most cases, the effect of the outer wave is stronger, and as a result, young Jupiter, instead of staying in place, began to slowly but inexorably drift towards the inner solar system. This process is called Type 1 migration. According to the Grand Tack model, developed by a group of astronomers from Nice, Jupiter began its journey from an orbit of about 3 astronomical units and moved inward. It crossed the region where the asteroid belt is located today. It continued its fall until it reached an orbit of about 1.5 astronomical units. This is surprisingly close to the Sun. This is the orbit of modern Mars. Imagine this picture. A giant Jupiter, 300 times more massive than Earth, invades the region where rocky planets were forming. The consequences of this invasion must have been catastrophic. With its monstrous gravity, it acted like a giant cosmic plow. It ejected countless planetesimals and protoplanets it encountered from the system. It disrupted forming orbits, sowed chaos and destruction. Many models show that if Jupiter had remained in this orbit, then Earth and Venus most likely would not exist today. It would have either absorbed them or ejected them from the solar system. But then the second giant, Saturn, came into play. It formed slightly later than Jupiter and was less massive, but it also began to migrate inward, following its older brother. And at some point, their orbits entered what is known as orbital resonance. This is a situation where the orbital periods of two bodies are related by simple whole numbers. In this case, Saturn began to complete exactly 2 orbits around the Sun in the time it took Jupiter to complete 3. This is a 3-to-2 resonance. When 2 giant planets enter such a powerful resonance, their gravitational interaction changes drastically. They begin to act as a single system, and the effect of this resonance was salvation for the inner solar system. The combined gravitational influence of Jupiter and Saturn on the gas disk changed the balance of forces. Now they were able to clear a common gap in the disk, a kind of void, and this stopped their inward migration. Moreover, the balance of torques changed. Now the outer parts of the disk began to pull this bound pair of planets more strongly than the inner parts. And the incredible happened. The migration reversed. Jupiter and Saturn, still in resonance, began to drift outward together, back towards their native orbits. This is the Grand Tack. Jupiter, reaching the orbit of Mars, turned around and swam back. Its return journey was no less dramatic. Passing again through the region between Mars and its current orbit, it scattered most of the remaining planetesimals there with its gravity. The Grand Tack hypothesis is not just a beautiful story. It elegantly explains several key features of our solar system that have long remained mysteries. First, it explains the small size of Mars. Mars is about 10 times less massive than Earth, although according to all formation models, it should have grown much larger. The Tack hypothesis says that Jupiter, coming so close, simply ate Mars. It cleared its orbital zone of most of the building material, preventing it from growing to the size of Earth or Venus. Second, it explains the existence and structure of the asteroid belt. Why did a fifth rocky planet never form between Mars and Jupiter? Because Jupiter plowed through this region twice with its gravity. It prevented planetesimals from gathering into a single body and ejected most of them altogether. Those that remained are our modern asteroid belt, a pathetic remnant of what could have become a planet. Furthermore, the hypothesis explains why there are two different types of objects in the asteroid belt: dry rocky asteroids in the inner part and water and organic-rich in the outer part. The model suggests that Jupiter, during its migration, scooped up and mixed objects from different parts of the solar system, creating this complex structure. Finally, it explains why our system lacks so-called super-Earths, planets with masses from 2 to 10 times Earth's mass, which, as observations show, are very common in other star systems. Perhaps they also began to form here, but were destroyed during Jupiter's great journey. Thus, Jupiter's giant size not only allowed it to become the king of the system, it made it its main sculptor. Its journey back and forth, its Grand Tack, shaped the appearance of the solar system that we see today. It was the reason why Mars is small, why the asteroid belt exists, and possibly why our Earth was able to survive and develop in a relatively calm environment at all. Jupiter's role as the architect of the solar system did not end with its migration and the dispersal of the protoplanetary disk. Its giant mass continues to influence everything that happens in our stellar home to this day. And perhaps its most famous and widely discussed role is that of a cosmic shield, Earth's protector. The idea is very simple and intuitive. Jupiter, being the most massive planet, has the most powerful gravitational field. Therefore, it acts like a giant cosmic vacuum cleaner, or, if you will, a goalkeeper. Most comets and asteroids coming from the outer cold regions of the solar system, the Kuiper belt and the Oort cloud, on their way to the Sun, are forced to pass by it, and Jupiter's gravity captures them. It either swallows them, causing them to fall onto itself, or, what happens much more often, it acts as a gravitational slingshot, altering their trajectory and ejecting them from the solar system forever. Thus, it sort of clears the space, significantly reducing the number of dangerous objects that could reach the inner solar system and collide with Earth. Without Jupiter, according to this hypothesis, our planet would be subjected to bombardment hundreds, if not thousands, of times more often, which, in turn, would have catastrophic consequences for the development of life. Perhaps life would not have been able to develop into complex forms at all under conditions of constant cataclysms. The most vivid and illustrative confirmation of this idea was the events of July 1994. In that year, astronomers around the world observed a grandiose cosmic drama live, the collision of comet Shoemaker-Levy 9 with Jupiter. This comet was discovered shortly before. Observations showed that even earlier, during a previous close approach to Jupiter, its powerful tidal forces had torn the comet's nucleus into about 24 large fragments, which lined up in a chain, like a pearl necklace. And in July of '94, this entire process crashed down on Jupiter. Over the course of a week, one after another, fragments of the comet, some of which were 2 kilometers in diameter, plunged into the giant's atmosphere. Each collision caused a flash, visible even through amateur telescopes from Earth. The energy of the explosions was unimaginable. By estimates, the explosion of the largest fragment was equivalent to 6 million megatons in TNT equivalent. This is hundreds of times more than the entire nuclear arsenal of Earth detonated simultaneously. After falling into Jupiter's atmosphere, giant dark spots remained for several months, some the size of our planet. This event became a sobering reminder of the forces at play in space, and it clearly demonstrated Jupiter's role. We saw in real time how it took a blow that, had it been directed at Earth, would have led to a global catastrophe and mass extinction comparable to what destroyed the dinosaurs. Jupiter literally saved us without even noticing it. For him, it was like a mosquito bite. After this incident, the idea of Jupiter the Protector became almost an axiom. It entered textbooks, documentaries, and became part of the rare Earth hypothesis, which states that for the emergence of complex life, a unique confluence of circumstances is necessary, and one of them is the presence of a gas giant in the system in the correct orbit. However, as is often the case in science, later and more detailed studies showed that the picture is not so simple and unambiguous. The story turned out to be more complicated. New computer simulations, made possible by increased computational power, forced scientists like Kevin Grazer to reconsider Jupiter's role. They began to model the movement of millions of hypothetical comets from the Oort cloud over billions of years in two scenarios, with Jupiter in our system and without it. And the results turned out to be counterintuitive. Yes, Jupiter indeed effectively ejects a huge number of comets from the system. In this sense, it undoubtedly acts as a shield, but its gravity also has an opposite dark side. It acts not only as a goalkeeper, but also as a cunning sniper. The fact is that some comets that are initially on safe, very distant orbits from the Sun and would never pose a threat to us, experience its gravitational influence when they approach Jupiter. And sometimes this influence is such that it does not eject the comet, but on the contrary, draws it inward, placing it on a short-period orbit that intersects Earth's orbit. That is, Jupiter's gravity can turn a harmless object into a potential killer. Thus, it works in both directions. It eliminates some threats, but simultaneously creates others. And when researchers calculated the overall balance in their models, they came to an astonishing conclusion. It turned out that the presence of Jupiter in the system hardly changes the overall frequency of collisions with Earth. Yes, it protects us from one type of threat, long-period comets, but it increases the number of other threats, short-period comets. In the end, one almost completely compensates for the other. Moreover, some studies show that in the very early stages of the formation of the solar system, Jupiter may have played an entirely negative role. Its gravitational perturbations were responsible for the so-called late heavy bombardment, a period about 4 billion years ago when the inner planets, including Earth and the Moon, were hit by a barrage of asteroids. It is believed that the migration of Jupiter and Saturn destabilized the asteroid belt and the Kuiper belt, directing this wave of destruction towards us. So, who is he, Jupiter? A protector or a villain, a savior or a sniper? Probably both. His role is dual. He is a powerful gravitational factor that simultaneously stabilizes and destabilizes the system. He creates order and simultaneously generates chaos. The truth, as always, turned out to be more complex than a simple and beautiful myth. But Jupiter's influence is not limited to its gravity alone. It is itself the center of an entire miniature system that lives by its own laws and hides within itself, possibly, some of the most intriguing places to search for extraterrestrial life. And this system is its retinue, its court of dozens of moons. Until now, we have talked about Jupiter as a lonely giant whose mass and gravity shape the destiny of the entire solar system. But this is only part of the truth. Jupiter is not a loner. He is the center of his own complex and amazing system. He is a true king, surrounded by a numerous retinue of dozens of satellites. To date, 95 have been discovered, and this list is constantly growing. But among all this swarm of moons, a quartet of special ones stands out. The true aristocracy of the Jovian world. These are 4 satellites that Galileo Galilei saw in his primitive telescope in 1610. Their discovery forever changed our understanding of the universe. They are Io, Europa, Ganymede, and Callisto. These 4 moons, which today bear the name of their discoverer, the Galilean satellites, are not just pieces of rock and ice. Each of them is a complex, unique world with its own geology, history, and mysteries. And altogether, they represent nothing less than a solar system in miniature. Their birth story, scientists believe, largely repeats the story of the birth of Jupiter itself and the planets around the Sun. When the young Jupiter was undergoing a stage of rampant gas accretion, it did not just suck it in. Part of this gas and dust, which had sufficient angular momentum, did not fall onto the planet, but formed its own miniature accretion disk around it. It was a reduced version of the proto-planetary disk from which all the planets were born. And in this disk, rotating around a hot, shining protoplanetary Jupiter, the same laws operated. Close to the giant planet, it was hot, and only satellites made of refractory rocky materials could form there. Further away, beyond the miniature snowline, the temperature dropped, and water ice was added to the rock. This is precisely what we observe today. The density of the Galilean satellites clearly decreases with increasing distance from Jupiter. Io, the closest to it, is a dense, rocky world, almost devoid of water. Europa, the next one, consists of a rocky core and a thick mantle of water, covered by an icy crust. And the farthest, Ganymede and Callisto, are worlds where ice and rock are roughly equal. They formed in the cold outer regions of Jupiter's mini-disk. This pattern is a striking confirmation of the general theory of planetary system formation. But the most interesting thing about these moons is not how they were born, but how they live now. And their life is entirely determined by their master, Jupiter. His giant size and gravity are the cause of one of the most amazing phenomena in the solar system: tidal heating. We on Earth are accustomed to tides in the oceans caused by the moon's gravity. But imagine what Io experiences. It orbits very close to a planet that is 318 times more massive than Earth. Jupiter's gravity acting on the side of Io closer to it is much stronger than on the farther side. This difference in pull constantly stretches and deforms the satellite. It is stretched into an ellipsoid, like a rubber ball. If Io's orbit were perfectly circular, this ellipsoid would always be oriented the same way, and nothing special would happen. But its orbit, due to the gravitational influence of Europa and Ganymede, is slightly elongated. This means that Io sometimes approaches Jupiter and sometimes moves away from it. And because of this, the degree of its deformation constantly changes. The entire moon is continuously kneaded, squeezed, and stretched like a piece of plasticine in giant, invisible hands. This constant mechanical friction generates a huge amount of heat inside the satellite. It is this tidal heating that makes Io the most volcanically active body in the entire solar system. Its interior is molten. Hundreds of volcanoes operate on its surface, ejecting fountains of molten sulfur into space to heights of hundreds of kilometers. The entire surface of Io is a hellish landscape of solidified lava flows without a single impact crater, because volcanism erases them faster than they can appear. But if on Io tidal heating created a fiery hell, then on the next moon, Europa, it may have created a cradle for life. Europa is covered by a thick, tens of kilometers, crust of water ice. But under this crust, as shown by data from the Galileo spacecraft's magnetometers and many other indirect pieces of evidence, lies something amazing: a global ocean of liquid salt water. Europa is too small and too far from the sun to retain heat in its interior for billions of years. This ocean should not exist. It would have frozen to the very bottom long ago. But it exists. And the reason for this is the same tidal heating. Jupiter's gravity constantly massages Europa's icy mantle and rocky core, releasing enough heat to keep the water in a liquid state beneath the ice shell. This subsurface ocean of Europa is one of the most intriguing places in the solar system. By estimates, it contains 2 to 3 times more water than all of Earth's oceans combined, and it has existed for billions of years. We have all 3 key ingredients that we believe are necessary for life: liquid water, an energy source, tidal heating, and possibly hydrothermal vents at the bottom of the ocean, similar to our black smokers, and organic molecules that could have been delivered by comets. This is why future space missions, such as Europa Clipper, are aimed at detailed study of Europa. We are seeking an answer to the question, can life arise in the dark, cold depths so far from sunlight, warmed only by the breath of a giant planet? Ganymede is the next satellite. It is a unique case. It is larger than the planet Mercury and is the only moon in the solar system with its own magnetic field. It is likely generated in its liquid iron core by the same dynamo mechanism as Earth's. Data also indicate the possibility of a subsurface ocean on Ganymede. Thus, Jupiter's size determines not only its own nature, but also the nature of its satellites. It is not just a gravitational center. It is an energy source that makes these distant icy worlds geologically alive and potentially habitable. Its greatness gives rise to a whole constellation of amazing and complex worlds. But to fully understand the uniqueness, or conversely, the typicality of our Jupiter, we need to take the last step. We need to go beyond our star system and see how things are in the Milky Way. For almost all of human history, the solar system was the only example for us. We studied our 8 planets and thought we understood the general principles of their structure. We built a coherent picture: small rocky planets near the star, large gas giants on the periphery. This scheme turned out to be logical and universal. Jupiter, for all its grandeur, occupied its rightful, predictable place in it. We thought that most planetary systems in the universe should be similar to ours. Everything changed in 1995. In that year, Swiss astronomers Michel Mayor and Didier Queloz, observing the star 51 Pegasi, similar to our Sun, discovered a planet orbiting it. It was not the first exoplanet discovered, but it was the first found around a Sun-like star. And this planet overturned all our ideas about what planetary systems could be like. The object, named 51 Pegasi b, was a real monster. Its mass was about half the mass of Jupiter. That is, it was undoubtedly a gas giant. But its orbit shocked astronomers. This planet orbited its star at a distance 20 times closer than Mercury orbits the Sun. A year on it lasted only about 4 Earth days. The temperature on its surface must have exceeded 1,000 degrees Celsius. It was a hot Jupiter, a gas giant that, according to all our theories, should have formed far beyond the snowline, in the cold outer regions of its system, somehow ended up practically in direct proximity to its star. The discovery of 51 Pegasi b was a true revolution. It showed that planetary migration, which we discussed in the context of the Grand Tack hypothesis, is not some exotic and rare phenomenon. It is most likely a fundamental process that occurs in most, if not all, planetary systems. It's just that in our system, Jupiter's migration stopped and reversed in time. And in the 51 Pegasi system, the giant did not stop. It plunged all the way to the star, most likely destroying all rocky planets that might have formed in its path along the way. Since then, thanks to the work of the Kepler Space Telescope and its successor TESS, we have discovered more than 5,000 exoplanets. And this enormous statistic has allowed us to look at our Jupiter and our solar system in a new galactic context. What have we learned? Firstly, we have learned that gas giants are quite common, but their location is a completely different story. It turns out that hot Jupiters, like 51 Pegasi b, are quite common. Warm Jupiters, orbiting at distances comparable to Earth's or Mars' orbit, are also common. But cold Jupiters, analogous to ours, i.e., gas giants on wide, nearly circular orbits located far beyond the snowline, turned out to be surprisingly rare. According to current estimates, only about 1 to 2% of Sun-like stars have a planet similar to our Jupiter in their system. This makes our solar system quite atypical. Most systems we see look different. They either have no gas giants at all, or they have migrated inward, disrupting the entire inner architecture. This discovery has enormous implications for the question of the search for life in the universe. There is growing evidence that the presence of a cold Jupiter in a system may be one of the key conditions for the emergence and long-term existence of life on Earth-like planets. Why? Firstly, as we have already discussed, such a giant, without intruding into the inner system, helps stabilize it. It does not destroy forming Earth-like planets. Its stable distant orbit does not create gravitational chaos. Secondly, its migration in the early stages, if it was similar to our Grand Tack, could have played a key role in delivering water to the young Earth. It is believed that Jupiter, scattering icy asteroids from the outer part of the system, could have seeded the inner planets with water and organics that became the building blocks for life. A hot Jupiter is incapable of this. Thus, our Jupiter is not just a big planet. It is a representative of a rare class of correct giants. Its size, its location, and the history of its migration seem to have formed a unique combination that made possible the emergence of such a complex and stable world as ours. Studying thousands of other worlds has allowed us to better understand our own. It showed that the answer to the question, why is Jupiter so big, is just the first step. The next, deeper question is, why is it where it is? And the answer to it seems to be closely related to the answer to the most important question. Why are we here? Our giant, our king and architect, turns out to be also our unlikely guardian. And realizing this role is one of the most profound insights that modern astronomy has given us. We have taken a long journey together. We began with a primeval molecular cloud, cold and empty. We saw how a protoplanetary disk was born from it. We crossed the invisible snow line that divided the world into the kingdom of rock and the kingdom of ice. We traced how Jupiter's embryo, thanks to the abundance of ice, quickly gained critical mass and won the race, eventually absorbing an immense ocean of hydrogen and helium. We saw how, becoming a giant, it embarked on a great journey through the solar system, forever changing its appearance. We plunged into its depths, where under monstrous pressure, hydrogen turns into metal, generating the most powerful magnetic field in the system. We admired its retinue, worlds of moons, warmed by its tidal breath. And finally, we looked at it from the depths of the galaxy and realized how rare and special it might be. Now, we can put all the pieces of the puzzle together and answer our initial question. Why is Jupiter so big? It is big because it was lucky enough to be born in the right place, beyond the line where water freezes. This gave it a huge amount of building material. It is big because it was lucky enough to grow quickly, faster than the Sun destroyed the protoplanetary disk. This allowed it to capture its gaseous envelope. It is big because the physics of accretion and gravity work exactly like that, launching runaway growth after reaching critical mass. But, as in any good scientific detective story, having found answers to some questions, we inevitably encounter new, even more complex mysteries. Our portrait of Jupiter is still far from complete. It remains unfinished. We still do not fully understand what exactly its core looked like at the moment of formation. Was it initially diffuse, or did it become so as a result of a giant collision? Juno's data gave us food for thought, but not a final answer. We do not know all the details of its migration. The Grand Tack hypothesis is beautiful, but it is just one of several models. What was its exact route? How close did it get to the Sun? Answering these questions means understanding the minutest details of our Earth's formation. We do not fully understand what exactly powers its giant storms, such as the Great Red Spot, a hurricane larger than Earth, which has been raging for centuries. What is its energy source? To what depth does it extend? We are only beginning to grasp the complexity of its satellite system. Is there life in Europa's ocean? How exactly does Ganymede's dynamo mechanism work? What lies beneath Callisto's surface? Jupiter is not just a planet. It is a natural laboratory where processes occur on a grand scale that we can never reproduce on Earth. It is an archive, holding in its depths information about the very first moments of our solar system's life. And it is an indicator that helps us understand our place in the universe. Each new mission, whether it be Juno, which continues its flybys over the poles, or future probes such as the European JUICE probe or the American Europa Clipper, adds new strokes to this portrait. But the more detailed it becomes, the clearer we see how many blank spots there still are. And in this, perhaps, lies the main charm of science. Cognition is an endless process. Jupiter, the largest and oldest of our planetary family, still holds its main secrets. It awaits new instruments, new ideas, new generations of researchers who dare to ask it the right questions. One wonders what incredible chapter in its biography we are yet to read. The question remains open.